Okay, so I am actually going to start chapter 5 today, which is about continuous random variables. So this is a very different sort of subject than the discrete random variables that we've been talking about. And in order to get started, I want to remind you something about discrete random variables. I want to summarize. Okay, so let's recall something about discrete random variables. Their properties. So you have a sample space with a probability rule, and then you have x is a function. X is a random variable, is a function from the sample space to the real numbers. Now it's a discrete random variable. It's a discrete random variable. If the values this function takes live in a discrete set of points, so it takes discrete values. So it doesn't contain an interval, for example. And we defined the PMF of a discrete random variable, the probability mass function, to be the function which is given by taking a real number a. It's given by the probability that x equals a. And this is shorthand notation for the probability of the event given by all elements of the sample space having the property that x of s takes value a. So that's the definition of the probability of x equals a. And likewise, we have the CDF, the cumulative distribution function, that's usually denoted capital F, and f of a is the probability that x is less than or equal to a, which is the same as the probability of the event given by the set of all s's in the sample space such that x of s takes value less than or equal to a. These are just the definitions. Now, in the discrete case, we can graph the CDF, and we saw that it always looked like a step function. So it looks like a step function. And then it's eventually zero outside of some region because we have to get an area underneath the CDF to be 1. Okay, so this is only in the discrete case this picture occurs. So what I want to talk about today is the continuous setting. But before I do, I want to remind you that that we can also define one other thing associated with the information. We could say that if B is any subset of the real line, we can define the probability that x takes value in B to be the probability of the event given by the set of all x in S such that x of x is in B. Oh, that's really bad. That's really bad handwriting. So let me reproduce that. Let's say it's the probability of all S in S such that x of S lies in B. And we know what this is given by. This is given by, it's really just a sum of P of x's where x lies in B. That's actually the same thing. So the point I'm trying to, this is what I want you to concentrate on. Think of this sum here as defining the probability that x lies in B. Okay, so this is all supposed to be some sort of motivation for what's coming next. So So what comes next is section 5.1. And the situation with 5.1 is the CDF will always have the following. It will always be continuous, so it's a continuous function. That's the basic idea. And we have to make some definitions. So we have the notion of a continuous random variable. That's a function from the sample space to the real numbers. And then we make a definition. So we have a function. So then this definition is this: there exists a. Oops, I don't want to use abstract mathematical notation. There is a function. This is maybe an axiom for what we want. F of x called a probability density function. I'll just say probability density. So this is going to be taking the place of the probability mass function. So probability density function, maybe I'll write the word function. F of x, which is defined on the real line such that for a subset B in R, a subset, think of an interval, the probability that x lies in B is given by the integral over B of f of x dx. So you're integrating over the subset B. B will be an interval typically. So this is essentially a definition of what it means to be a continuous random variable, and f of x will be a continuous function. So f of x should be continuous. Okay, so that's the definition. I want to sort of essentially get some consequences of the definition, immediate consequences. Okay, so the first immediate consequence is that if we look at the probability that the random variable takes any values, that would be x in R. R is the entire subset of the real numbers. That has to be 1, so that tells us that the integral from minus infinity to infinity of the probability density function is equal to 1. This should remind you of what we did way back when. Should remind you of the sum of the probability mass functions P of x is 1. This plays the role of that. We're integrating, which is like a generalized sum. Okay, so that's the first thing. The second thing is, the second main property of it is that the probability that x lies between two given values a and b is the integral from a to b of f of x dx. Okay, and by the way, the first property is saying that the area under the curve f of x, the area under this curve is 1. Area equals 1. Okay, so, and then the third property, which we can deduce from the second property, is the probability that x takes, this is going to be very different than in the discrete case. The probability that x takes a single value a, that's the probability that a is less than or equal to x is less than or equal to a, of course, and that's the integral from a to a of f of x dx. But if you integrate a function between with the same limits of integration, you always get 0. There's no area generated by that. So this is very different. Now, what's an example to have in mind before we go on of such a thing? Well, you could think of the case, an example of a spinner where you spin a dial around and around, and it can take any, where it points will be the value of the function f of x, and if you spin the dial, the probability that any one value occurs is probability 0, because there's a whole interval, there's a whole circumference of a circle of possible values that can occur. Another example of a continuous random variable is a temperature reading, where if we allow the temperature to be any real number, usually human beings, we truncate the real number and say it's 37 degrees or whatever, right? But in fact, the temperature could be any real number. Okay, so that's an example of a continuous random variable. It's a measurement of temperature, or the spinner points. Okay, so the last property I want to mention right now for today, there are other properties that we have to look at, but the last one is that if we want to compute the CDF, cumulative distribution function, it's given by the probability that x is less than or equal to a, and that's the integral from minus infinity to a of the probability density function. So this is an important feature. This is a definition, if you like. We can make this a definition. Okay, so what I'd like to do is just talk about some examples right now of such things, just to give you a feel for it. So this is really just some version of ordinary calculus 2 that we're talking about now. This is what you have to know is calculus 2 to understand most of what goes on. So here's an example. Consider the following function, f of x equals, so a probability density function is always non-negative, and the area under the curve between minus infinity and infinity is 1. That's the definition. And so here's an example. Let's try f of x equals 0 if x is less than or equal to 1, and it's 1 if x is greater than 1. So, oh, that's a bad example. 1 over x squared. That's a good example. So let me graph this. Here's a graph. So this is 1 over x squared. So it's going to look like this for x bigger than or equal to 1. So looks like this, and then it's got value 0 below that. Okay, so that's the graph of our curve, and I want to verify it's a probability density function. So what I have to do is compute the integral from minus infinity to infinity of f of x dx. But the area of this curve for x less than or equal to 1 is below less than 1 is 0. So it's really the integral from 1 to infinity of 1 over x squared dx we're computing. So that's x to the minus 2. So the antiderivative is minus 1 over x. And we have to evaluate it. This is an improper integral, so I'm going to evaluate it from 1 to t and then send t to infinity. And this becomes what? This becomes minus 1 over t. It's going to be the limit as t goes to infinity, minus 1 over 1. And we're going to take the limit as t goes to infinity, and this is going to give me plus 1, which is what we needed to get. So this checks out. Okay, let's compute for this example the probability. Let's compute the probability that 1 is less than or equal to x is less than or equal to 2. What do we get? Well, this is the integral from 1 to 2 of f of x dx, which is the same thing as the integral from 1 to 2 of 1 over x squared dx, which is going to be given by minus 1 over x from 1 to 2, which is given by minus a half minus 1. So that's looks like you get a half here. So that's a half is the answer. Great. Okay, so that's an example. By the way, another property that's useful, let's call it property 5, is that if we take the cumulative distribution function, let me not state it this way, what I'm going to do. If we took it the probability that x is less than a, that's the same as the probability that x is less than or equal to a. This is only true in the continuous case, and here's the reason. Here's the reason why. Because this is the same thing as the event that x, oops, I didn't, let me do it on this side. The latter is the probability. So we're asking whether this is true. It is true, but I'm going to show you why. This is the same as the probability that x is strictly less than a or x is equal to a. But these are mutually exclusive events. So this is the same as the probability that x is less than a plus the probability that x equals a. But the probability of x equals a we saw was 0. So it's the same as the probability that x is less than a. So this is only true in the continuous case, not in the discrete case. Okay, let me give you another example of a probability density function, which is this. Let's look at f of x equals 0 if x is less than 0. And lambda e to the minus lambda x if x is greater than or equal to 0. And here lambda is some real number, some real number that's non-negative. It's just a parameter. This is called the exponential distribution. And it's usually used to model waiting times or things like light bulb, how long a light bulb will last. And so this is a very useful distribution. And I claim it is a probability density function. So let's see why. This is a PDF I'm claiming. So in order to do that, I have to show that it's certainly non-negative. I just have to compute the integral of from minus infinity to infinity of f of x dx, and I better get 1. But this is the same as the integral from 0 to infinity of lambda e to the minus lambda x dx, because for x less than 0, the value of the function is 0. And this is the same as the limit as t goes to infinity of 0 to t of lambda e to the minus lambda x dx. And you're going to get, when you integrate, you're going to get, it looks like it's going to be minus e to the minus lambda x evaluated from 0 to t. And that's the limit as t goes to infinity of, I'll put the minus sign outside, e to the minus lambda t plus, I'm sorry, minus, it should be a minus here, minus 1. And so you compute the limit, this term over here tends to 0 because lambda is positive and t is going to infinity. And so you're going to get plus 1. And that's correct. That's what you need to get. So that's an example. Let's compute a sample example of probability for this distribution. So in this example, compute the probability that 0 is less than or equal to x is less than or equal to 2. Well, that's the integral from 0 to 2 of f of x dx. But if you remember what the function was, for x bigger than 0, you get lambda e to the minus lambda x dx. And so you're going to get minus e to the minus lambda x from 0 to 2. And if you evaluate that, you'll get 1 minus e to the minus 2 lambda. That should be the answer. Okay, so that is another example. And then I want to do one more thing today, which is how to sort of take a random variable which is continuous and make another random variable and see how the cumulative distribution function changes. And I'm just going to do a very simple example today. We're going to work on this more systematically next at some future time. So this is directly in the book. This is example 1D in the book in the section 5.1. So let x be a continuous random variable with CDF, cumulative distribution function, f sub x. We're using x in the notation to distinguish it from some other continuous distribution function, and probability density function, little f sub x. And so let's set y equal to 2x. And the problem is compute the PDF of y. So that's the problem. Okay, so this is not hard. It's just a rephrasing of a lot of definitions. So what is the PDF of y? Well, let's let f sub y equal the cumulative distribution function of y, and let lowercase f sub y equal the PDF of y, the probability density function of the random variable y. Okay, so what is f sub y of a number a? Well, it's by definition the probability that y is at most a, but that's the same thing as the probability that twice x is less than or equal to a, which is the same thing as the probability that x is less than or equal to a over 2. But the probability that x is less than or equal to a over 2 is precisely the definition of the cumulative distribution function of x evaluated at a over 2. So we get this equation that relating the cumulative distribution function of the random variable y to the cumulative distribution function of the random variable of x, of the random variable x. Now we're going to differentiate, take the derivative of both sides of this equation. If we take the derivative of the left side, what do we get? Well, we're going to get fy of a prime. And on the right side, by the chain rule, the derivative of the right side with respect to the variable a is 1/2 the derivative evaluated at a over 2 of the CDF of the random variable x. Now, we have to go back, and I should have done this. This should be probably property 6 I'm going to talk about here. So property 6 is this, that if we look at, remember what if we have a CDF that's given by the integral from minus infinity to the variable a of f of x dx. So by the fundamental theorem of calculus, f prime of a is given by the integrand evaluated at a. This is the fundamental theorem of calculus. So the derivative of the CDF is the PDF. So that means that the left side of this equation on the left side of the screen is given by f sub y of A, and the right side is given by 1/2 the PDF of the random variable x evaluated at A over 2. So that is actually the answer to our question. The PDF, the probability density function of the random variable y evaluated at a number A is 1/2 that of the probability density function of the random variable x evaluated at A over 2. So, and this property that we just derived, that this one here, this is very important. The derivative of the CDF is the PDF. This is property number 6 of the basic properties that I wanted to mention today. Okay, so that's enough for today. Have a good day.